In this video, I am going to explain second order homogeneous recurrence relation. Okay. Now consider one equation of the form Cn into An plus Cn minus 1 into An minus 1 plus Cn minus 2 into An minus 2 equal to 0 for n greater than or equal to 2. This is the second order homogeneous recurrence relation, okay, where this Cn and Cn minus 1, Cn minus 2, they are all constants and they cannot be 0, that is Cn cannot be equal to 0, this first term. Now this is the equation which is related to quadratic equation. You may remember it as ax square plus bx plus c is equal to 0. This is the quadratic equation. Why we call it as quadratic equation? Because highest degree of this x is 2. Now if I put a is equal to 0 in this equation, then it will be b, obviously this term is going to be 0, so we will be left with bx plus c is equal to 0, and it is not quadratic equation. So that is why here this Cn cannot be equal to 0. Okay, that's why I have this condition. If Cn is equal to 0, then it will not be second order homogeneous recurrence relation. Okay. Then let us put An is equal to c k raised to n. Whatever previously we have seen, where c is not equal to 0 and k is not equal to 0. If I put like that, then it will be Cn. Instead of An, we are going to put C into Kn. And Cn minus 1 was already there, but we have An minus 1. It means that C as it is, so K raised to n minus 1. Then Cn minus 2 as it is, but instead of An minus 2, where is it? Well, here. Instead of An minus 2, I will put C into K raised to n minus 2 equal to 0. Okay. Now if I simplify this, it will be Cn k square plus Cn minus 1 k plus Cn minus 2 is equal to 0. So how I have got this equation? I have simplified here. So here actually we have k raised to n. Then we are dividing entire thing by, all terms by k raised to n minus 2. Okay. If I divide it by k raised to n minus 2, then kn will be, if I divide kn by kn minus 2, k to the power n minus 2, then it will be kn. I can write this term as kn into k raised to minus 2. Then these two terms get cancelled. Then 1 divided by k raised to minus 2, it will be k raised to 2, that is k square. That's why I have written k square here. Similarly, you will get k, and the term will be vanished. If you divide it by k raised to n minus 2, then these two get cancelled. Then you will be left with only c n minus 2 equal to 0. Now this equation 2 is called as characteristic equation or auxiliary equation. Okay, remember this. This is characteristic equation of second order homogeneous recurrence relation. So now depending on the roots, now you have come across again that quadratic equation. There will be three possibilities. That is, first possibility is roots are equal and distinct. Real and distinct. Then second case is roots are real and equal. And third case is roots are complex or roots are imaginary. Depending on these three, we have some different solutions. Now what if roots are real and distinct? If roots are real and distinct, then what we do? This is the formula. An is equal to a k1 raised to n plus b k2 raised to n, where a and b are some constants, real constants. Case 2 is roots are real and equal. If it is the case, then we write an is equal to a plus bn into bracket k raised to n. Then if we have roots as imaginary, then we write k1 is equal to p plus iq, k2 is equal to p minus iq. And in that case, we are going to write an as an is equal to r raised to n into bracket a cos n theta plus b sin n theta. Okay, and where r will be k2, I mean k1 equal to k2 equal to, we will find it as p square root of p square plus q square, and theta will be calculated as tan inverse of q divided by p. As of now, you don't bother about this imaginary part. Let us try to solve one simple example on this, then it will be more clear for you about second order recurrence relation. Solve the recurrence relation an plus an minus 1 minus 6 an minus 2 equal to 0 for n greater than or equal to 2. So when it is n greater than or equal to 2, it means that it is second order and it has started from an minus 2, an minus 1, an minus 2 equal to 0. Given that a naught is equal to minus 1, a1 is equal to 8. Okay, let us try to solve this. Now first identify coefficients of an minus 1, an minus 2. What is the coefficient of an here? If there is no term, means it is by default 1. So 1 is the coefficient of an. Now what is the coefficient of an minus 1? Even it is 1. What is coefficient of an minus 2? It is minus 6. So 1, 1 minus 6 are the, see here I have written cn is equal to 1. It means that 1 is the coefficient of an. 1 is the coefficient of an minus 1. Minus 6 is the coefficient of an minus 2. Okay. Then we write characteristic equation as we have written here, equation number 2 here. So let us try to in terms of k. Okay, cn then k square plus cn minus 1 k. Similarly, we will write for this equation or this example, where is it, here, k square plus k plus constant is equal to 0. Coefficient of k square is 1, that is cn. Coefficient of k is also 1, that is cn minus 1, and minus 6 equal to 0. Now I can write this as k square is equal, k square plus, I can split this k into two terms, 3k minus 2k, and minus 6 as it is equal to 0. Then I'll take k common in the first two terms, then it will be k into k plus 3, minus 2 I'll take common from these two terms, then minus 2 into bracket k plus 3 equal to 0. Then it will be k plus 3 equal to k plus 3 into k minus 2 equal to 0. Therefore we will get k is equal to minus 3 and k is equal to 2. So these are the roots. Now if you observe, roots are real and they are different or they are distinct. So this is the case 1. So for case 1, what was the equation for an? Here it is, an is equal to a k1 raised to n plus b k2 raised to n. So it's the same thing I am going to use here. See, when roots are real and distinct, then we go for an is equal to a k1 raised to n plus b k2 raised to n. A is unknown as of now, so a you write as it is. Now this term k is minus 3, k1 I can write this, okay, minus 3 plus b k2 I have taken it as 2. Now a naught is equal to a into bracket minus 3 raised to 0, because for n is equal to 0 I am considering it, okay, plus b into this 2, k2 is 2 raised to 0. Then I will get a naught as a plus b, because anything raised to 0 is 1, here anything raised to 0 is 1, so a plus b. Therefore I can write a plus b is equal to minus 1, because a naught value is given. A naught is given in the problem statement itself. Here it is, a naught is minus 1. Therefore this a plus b is equal to minus 1. Now let us consider a1, because a1 is also given. If I put n is equal to 1, then I will get this equation, a1 is equal to a into bracket minus 3 raised to 1 b into 2 raised to 1. Now if you solve this, put a1 is equal to 8 equal to minus 3 as it is, 3a plus 2b. Now minus 3a plus 2b is equal to 8. So now let us solve these two equations simultaneously. Then I will get, see here, whatever is 3a plus 3b minus 3 is equal to, here what we have done is, second equation is this one, minus 3a plus 2b is equal to 8. But first equation is a plus b equal to minus 1. So we are multiplying equation 1 by 3. So I will get this 3a plus 3b is equal to minus 3. If I multiply this equation by 3, then I will get this one. So if I solve these two equations simultaneously, then I will get 5b is equal to 5, then b is equal to 1. You put it in some equation like a plus b is equal to minus 1 we had, equation number 1. Then thereby I will get a is equal to minus 2. So finally I can replace these a and an values in this equation, or an. It will be an is equal to, already equation is this. So you will get minus 3 raised to n plus 2 into 2 raised to n. So for case 1 we had an is equal to a, this k1 raised to n plus b k2 raised to n something. So if you put all, replace all values of values of a, b, k1, k2, then finally you are going to get this an is equal to minus 3 raised to n plus 2 into 2 raised to n. So this is the required solution for the given problem. Thank you.